Good afternoon, everybody. Welcome to this week's Geotalk. Thank you for those of you who have joined us in the room. And enjoy your beers, courtesy of CCIC and John Hancock's. Thank you, John, for sponsoring these real beers. We haven't got to chips yet, but we'll get there soon. So welcome, everyone, and to everyone online watching on Zoom and watching on YouTube. Thanks for joining us. And welcome to Allan Wilson, who is giving this week's Geotalk. Allan is an emeritus professor here in the School of Geosciences and has been here since 2006. He joined us from UKZN, where he was the head of school and where he worked for several years. And as you'll know, Allan Wilson has worked on South African geology and Southern African geology for a very long time on a range of different topics related to the Bushveld complex, KOMATIITES, the Great Dyke, and many other really interesting magmatic phenomena. And as you'll see tonight, he's going to be talking specifically about KOMATIITES. And as you also probably know, Allan, when he joined Wits Geosciences, started a very strong ICPMS and XRF laboratory known as the Earth Lab, which continues today and is growing year by year with new instruments. And so that was a fantastic foundation that Allan set up when he arrived at the school, for which we're very grateful. So without further ado, I'm going to welcome Allan to the stage, but I just wanted to also mention that what Allan will talk about tonight is not yet published. And so often we listen to Geotalks where the material is already published or a student has submitted a thesis. This is not even on the press yet, it's in press. So we're hearing science that hasn't seen the light of day yet. So Allan, thank you for being willing to do that, and everyone enjoy this really novel, exciting science. Right, let's get Allan's. Okay. Allan, over to you.
Thank you, Grant. Thank you very much. Well, it's quite an honor to be one of the first giving a live talk here after what seems like years, but it's very nice to see people here. So I'm going to be talking about olivines in KOMATIITE from the Archean deep mantle and some attributes there. So let's talk a little bit about KOMATIITES. What are KOMATIITEs? KOMATIITEs are high magnesium magmas that reflect the state of the mantle in the earliest stage of Earth's history. KOMATIITEs are the hottest magmas ever to have formed on the planet, and they are host to extensive magmatic ore deposits in certain parts of the world. They're mainly restricted to the Archean, but there is evidence of recent eruption of KOMATIITEs. They continue to erupt at present in some parts of the solar system, as I will show you. KOMATIITEs contain olivine, which potentially carries a signature of every magmatic stage. Olivine is like a god's mineral. It really is. And KOMATIITEs were first discovered in South Africa by Morris and Richard Viljoen over 50 years ago, but it was suggested by Otani way back in 1995 that KOMATIITE had an origin in the mantle transition zone, but this never was substantially proven. So where do KOMATIITEs occur worldwide? This is from Nick Arndt's book, and you can see they occur all over the world by the red dots, but they mainly occur in Archean cratons. The only exception is really these ones over here, which are part of the Caribbean plate, Gorgona and some other occurrences in this area, but all the others occur in stable cratons from the Archean, excellent exposures in India, the classic areas in Australia and in Canada. And of course, our KOMATIITE in the Karpal craton. Do KOMATIITEs occur in other planetary systems? Yes, they do. And in fact, they occur on the moon of Jupiter called Io. And this was imaged and spectrally analyzed by the Galileo spacecraft in 1995 with measured temperatures of 1500 degrees centigrade and high reflecting magnesium lavas. And it's very opportune at this moment that a new space probe called Lucy has just been launched a couple of days ago. So we wish Lucy all the best in getting back to Jupiter. She will not be looking at the moons, but at the Trojan assemblage, which follows Jupiter around. Location of greenstone belts and komatiites in the Carpal craton. Most of these host komatiites. These are in green. Of course, the classic is Barberton over here. And then these areas over here are all greenstone belts. And I've outlined them here in red, where you can see the occurrence of these greenstone belts. And the one I'm going to be talking about mainly today is a 3.3 billion year old COMMONDALE greenstone belt. Now, what's interesting is that the COMMONDALE greenstone belt has unique lavas, unique compositions. But we are now finding these same types of compositions elsewhere. And in fact, working with Sebastian and Tendo from UJ, we've discovered them way down here in the Buffalo River. And there have been recent papers from the San Francisco craton in South America, where there are similar komatiites. Okay, let's talk a little bit about olivine. Olivine, I think, I would like to call it the high temperature magmatic note keeper. It's the first phase to crystallize in all mafic magmas. It directly reflects melt compositions and conditions. It has a simple, robust structure that encapsulates, strong enough to encapsulate melt inclusions, which is a key to understanding the melts that are in equilibrium with olivine. There are highly contrasting controls on the included trace elements in olivine, and these have very, very variable diffusion rates, with lithium and sodium much greater than magnesium and iron, and going all the way down to the elements which have got very, very low diffusion coefficients, aluminium and phosphorus. Now, this is crucial to actually understanding how olivines form and what information they can tell us. Each element potentially records a different stage of the magmatic process, with the slow diffusing elements the most useful. But olivine preservation is a problem in ancient rocks because it weathers extremely easily, particularly the very high magnesium olivines. So what do Barberton komatiite flows look like? Let's start specifically looking at some of these flows. This is a classic texture of komatiite from Barberton. And what you see is there are different layers in this called the A series of layers and related over here. These are spinifex. This is a highly elongated, rapidly cooled crystal structures, and they overlie the B zone, which is this part over here, and which is very different. So right now then, you can see that it's a very asymmetric structure to Barberton lava flows. But the question that I'm going to look at now is, where did these cumulate olivines come from? Okay, so I'm not going to talk too much about olivine, well, I'll be referring it, too much about Barberton, but I will be referring it to now and again. So where did these cumulate olivines come from? And even though the komatiites were discovered 50 years ago, we are still grappling with this exact issue. Now, let's look at COMMONDALE. This is what COMMONDALE looks like. From drone photographs, you can see the flow structures here, very well defined, but not continuous. And the only way we can study these lava flows in detail is by drill core. And drill core is what this talk is based on. Also, they're very interesting small scale layering, which we have never fully understood, and nobody knows exactly how they form. So what we look at here is a structure of a COMMONDALE lava flow with fine-grained chills, spinifex, and what I've called ferric olivine in the center. I choose not to use the term cumulate anymore on these rocks because they're not cumulates in the true sense. But the important thing is this is almost a symmetric flow section, very different to Barberton. This is some of the textures that one would see in olivine ferric komatiites. This is Berlingui and COMMONDALE on this side over here. And what you see in Berlingui is that these have some extremely well-shaped crystals, euhedral, skeletal crystals, that compared in, and enclosed within this dark matrix, which is a komatiite glass. Now, COMMONDALE is quite different. These are much finer grained, as you can see from the scale here. The crystals are rounded, and they are contained within a more felsic matrix, even though these are extremely high. The rock is extremely high magnesium. And this will explain some of the features that we see a bit later in the talk. But that shows the difference between COMMONDALE komatiites, the olivine ferric textures, and those in Berlingui, which are often taken as the most typical example and best example of komatiites. Okay, types of komatiites. There are several different types of komatiites, and these are called aluminium depleted, aluminium undepleted, aluminium enriched, and super depleted. And all of these types are seen in Barberton. Here we see Barberton aluminium depleted. There are the aluminium undepleted. There are the Barberton aluminium enriched. And these are the super depleted komatiites with extremely high aluminium titanium ratios. So where did these come from? Now there is a group in Barberton called Mendon Formation where you have similar compositions, but there are no fresh olivines in any of the Mendon rocks. Let's look at the rare earth pattern over here, and we see that most of the classic komatiites are shown up here with slightly different, well, quite different patterns. There's Barberton aluminium depleted, there's Barberton aluminium undepleted. This is Berlingui over here, and this is Munro Township from Canada. Then you see COMMONDALE is completely different, extremely depleted in the light rare earths, but not so much depleted in the heavy rare earths. Now there's only one assemblage you can actually melt to get this type of pattern, and I'll talk about this as we a bit later in the talk. Okay. Volcanic eruptions are often catastrophic. As we know right at the moment from contemporary and present day La Palma eruption, every day on the news you see this amazing building process of the Canary Islands, and this eruptions at a temperature of 1240 degrees. Now the reason I'm telling you this is that the COMMONDALE lava erupted at 1700 degrees. That's nearly 500 degrees hotter than what's happening in La Palma, and they had a flow speed of 200 kilometers an hour because the viscosity was so low that these things would have been, COMMONDALE lavas would have been like lava tsunamis. And instead of red heat, they would have been white, and when cooled, the lava would also have been white because there's very little iron in these rocks, and there's no surface oxidation. So it would have looked like ice. Now we have a diagram here which relates olivine compositions to whole rock chemistry. So this is iron in whole rock and magnesium in whole rock on this axis over here. And these are lines which show compositions of olivines would be in equilibrium with any melt controlled by the iron and the magnesium. So any melt composition would, lying on this line over here, would crystallize olivine of forsterite 89. Similarly over here, forsterite 95 would crystallize from any melt which lies along this line over here. Okay. Now, on this diagram, what I've got here is some of the classic komatiites. Here's barberton, shown by this symbol over here. That's a melt composition. This composition over here is Alexo in Canada, shown by that symbol. And then Bilingue is over here, and Tortugal in the Caribbean is over here. And then the rock types associated with these occurrences, the whole rock chemistry, whole rock compositions are shown by the symbols. There's the Caribbean, there's Bilingue, the open circles here are Alexo, and these little crosses are barberton. Now, the COMMONDALE melt has this composition over here, 36% magnesium, 6.7 iron. It has the lowest iron ever recorded in a melt. Okay, remember these are accumulates, okay? So these are not melt compositions. These are the melt compositions, these symbols and squares. So 36% is the most magnesium lava, most magnesium komatiite ever described. Okay, so, and this line over here would be the evolution line by fractionation from the komatiite melt, which is lying over here. But what you see here is that on this equilibrium diagram, the COMMONDALE melt predicts a olivine composition of greater than forced-right 96. These are the most magnesium olivine forced-right compositions ever described. Okay, now it's the same diagram. And what I've shown here are three flow units in COMMONDALE by the red symbols, the purple symbols, and the black. And what you see is that they lie on very different control lines. They all come from very close to the predicted composition of, or the position of the COMMONDALE melt, which is over here, but they have very different lineages or lie on these different controls. So what is happening here? And what you see over here is that this composition predicts, or this line here of data from a single flow. These are 3 single flows in COMMONDALE. That projects to forced-right 96, exactly what is predicted by the olivine equilibrium over here, but these ones are not. These ones show much lower forced-right composition, or they lie along a line showing different forced-right olivines. So what are these things? These are mixing lines for primary COMMONDALE melt and mixed with olivine crystal populations from these 3 different flows. This tells us that every COMMONDALE flow has a unique chemical signature and a different combination of olivine crystals. So this flow over here, shown by the red dots, has got a much higher proportion of much lower forced-right content, olivines, than this one, and of course the highest one over here. Now these also happen to be this one happens to be the thickest flow, 25 meters thick. And I'm not going to go into this, but this has an absolute crucial control over how these olivines are accumulated. But every flow is unique. So if I take another set of flow compositions, it might lie over here, and another one might lie over here. I'm just saying it's an example of 3 at this moment. Okay. So the next thing we need to look at here is element diffusion rates in olivine. Now, I gave you a little bit of a preliminary on this earlier, but what we see here, because this is a log scale, it means the highest diffusion rates have lower numbers here, less negative numbers. These ones have very low diffusion rates, and it's also strongly temperature dependent. So lithium has a much higher diffusion rate than iron and magnesium and nickel, and there's calcium and chromium and aluminium. And what we see is that aluminium is basically 2 orders of magnitude slower diffusion rate in olivine than iron and magnesium. So this tells us then that iron, magnesium, and forced-right can equilibrate relatively rapidly in olivine, but aluminium cannot, which then has the potential to preserve original chemical signatures. And this explains the observed decoupling of forthright and aluminium in COMMONDALE olivines, which I will show you now. So this is now a study on the compositional profile across a single grain. This is an olivine grain over here. This is a typical texture. It's not exactly the same grain, but it's very typical, very similar to it. And what we see over here are the compositions across this olivine grain. So this is called zoning. And here is zoning for forthright. And you'll see it's very high. This is not the highest olivine, but this is the one I did a detailed study on, forthright 94. It's still very high. So it shows the core very high, and it rapidly drops off to very low forthright contents of forthright 86 towards the margin. But if you have a look at aluminium, it is almost constant across the grain at about just over 0.2% of aluminium oxide, decreasing significantly only at the margin. So there is very major decoupling between forthright and aluminium. Now this immediately tells you something. It tells you that the diffusion control is what is causing this decoupling. And the other elements are similar. There's chromium, very high chromium. And here's nickel. Now nickel does not follow forthright because this is a classic texture. This is a classic compositional relationship in most olivines is that nickel follows forthright. But here it actually cuts across the trends of forthright and nickel. Right, now this is probably the most important slide of the whole talk. And what you see here is examples from single crystals from two samples, two slides. In a single slide, this is the compositional profile of aluminium against forthright. And you can see it's almost constant here at this very high level, but forthright decreases very rapidly. So this is what I was showing in the last slide. And if you take another crystal in that same slide, you get a slightly different aluminium content. And if you take another one, and here they're quite low. So every single crystal is unique in its own compositional profile. And here's another sample shown on the black dots here, shows the same type of thing. So that means that in this sample, every single olivine is unique. It's got its own compositional profile. If you put all of these together, this is this diagram over here. So these are all the olivine data for COMMONDALE, shown in the yellow dots. And and it's compared with BARBERTON and these various greenstone belts and komatiite occurrences in the Caribbean, Alexo in Canada, Bilingui, and you can see that they are all relatively low, all less than 0.1% Al2O3, whereas the highest COMMONDALE olivines are over 0.3%. Now, this is highly significant. And the first thing is that these are the highest aluminium contents ever measured in an olivine, in any olivines. So how do we now use these data? Well, we can produce, aluminium in olivine is strongly pressure and temperature dependent, as was very eloquently demonstrated way back by Agee and Walker, where the partition coefficient between olivine aluminium and the melt, the aluminium in the melt, is defined in terms of pressure in gigapascals and temperature. So using the COMMONDALE olivines, you can predict a decompression path for the Commondale plume. And you can see the range up to here using this equation and knowing the composition of the Commondale melt. The temperature, the pressure we get is 10 gigapascals, and 1 gigapascal is 30 kilometers approximately. So this comes from 300 kilometers depth. And this decompression path then comes right the way down to surface at 0 atmospheric pressure, where the eruption temperature is 1,700 degrees. There are other parameterizations which give even higher pressures, because there is very little experimental work done on this range of olivine compositions, because measuring aluminium is very difficult at very low levels, and experimentally it's very difficult to carry out these types of experiments. Now, coming back to the rare earth pattern in the whole rock, well, this is the Commondale primary melt. And how do we get this extremely depleted rare earth pattern? Well, the only way you can reproduce this is by extreme compositions. And these are using this assemblage over here, wadzleyite, garnet, and calcium peroxide, which are the diagnostic minerals in the mantle transition zone. And you can see for garnet, they have extreme ranges for the partition coefficients, and calcium peroxide has very high partition coefficients, and which would lead to, if a calcium peroxide would have the ability to retain these highly incompatible elements. So putting this together, what we have here is a synoptic diagram of a Commondale plume. And here on the left side, we see the phases which make up the mantle profile with olivine and garnet at lower pressures, and then at higher pressures in the mantle transition zone, you get the minerals wadzleyite and ringwoodite. Wadzleyite and ringwoodite are high pressure polymorphs of olivine. Now, what's unique about the mantle transition zone is that it's hydrated. And there's more and more literature coming out on the amount of water that can be contained within wadzleyite and ringwoodite. So recently, or a few years ago, with Sobolev, we published a paper showing that the mantle transition zone reflected the, let's say, inclusions in olivines from BARBERTON reflected the water content in the mantle transition zone, some of which may have been derived from a subducted slab, not suggesting that plate tectonics is operating, but there still may have been subduction and some form of impingement of surface water right down to the transition zone, even in the early Archean. So what we have to have here is a first melting stage. Now, this is a plume coming from wherever. We don't know where these plumes come from. Some come from the core mantle boundary. Other Wyman believes that they actually generate only in the transition zone. But first stage melt will produce a residue depleted in incompatible elements and iron. Now you can immediately see where this is going. The Commondale komatiites are the lowest iron contents of any komatiites, and they are highly depleted. If you melt this residue again, it'll produce a Commondale melt. But wadzleyite, the high pressure polymorph of olivine, will be there because it's a very high temperature phase. So looking at this, and what we get is the first stage melting of the residue, a Commondale primary melt at 2000 degrees, which is much higher than ambient temperature, which I put as 1800 degrees. The top of the mantle transition zone at the moment is about 1650, but I think it's generally well considered that the mantle was considerably hotter. The ambient mantle was considerably hotter in the Archean. So Taking this further then, this melt then starts coming up furiously, rapidly, because it's got water, it's extremely hot, extremely low viscosity, and it's carrying up this COMMONDALE melt with some Wadsleite, and the Wadsleite rapidly converts to xenocrysts of olivine. Now, how these survive, we don't know, and this is an inference at the moment that the highest aluminium olivines are in fact the remnants of Wadsleite from the deep mantle. But what's more interesting, or just as interesting, is that as this melt comes up, it's also crystallizing olivines all the way up, and these are providing a pressure monitor right from the deep mantle near the transition zone right up through into the komatiites that have been erupted. So this is again a synopsis over here. This is the same diagram, but I want to show you here. This is then what this would look like. This is the assemblage of all of these olivines of different aluminium contents reflecting different pressures as these magmas, as this COMMONDALE magma came up and carried these different crystals with it. So what we see here is a high pressure, this is it's kind of idealized diagram, a high pressure olivine phenocryst with very high aluminium. Then we get a medium pressure olivine phenocryst, lower aluminium. And then we get a low pressure olivine phenocryst over here. And then these are all surrounded by this blue mantle over here, which in fact is the low pressure, low force right olivine rim, where you saw all of those compositions that I showed you earlier coming down to very low aluminium contents at very low force right content. So every one of these olivine crystals carries its own unique signature from the deep mantle. But what's even, well, another interesting point is we don't know how these things were transported actually in the flow itself. And what you see here is we get rings of olivines over here, and maybe a bit of imagination required, but I think it's fairly clear that these are rings of olivines. We have no idea how these form, but it's probably due to surface tension effects in a very, very low viscosity magma at very high temperature. So what does this crystal cargo, the olivine crystal cargo in KOMATIITES tell us? Firstly, these are all the compositions of the olivines, and this is not a normal distribution. It's highly asymmetric and shows completely different features. This is for 480 crystals measured. So the lowest aluminium would be near surface within the flows. These are phenocrysts that actually formed within the flows. Then we have a group of 0 to 4 gigapascals, which is up to 110 kilometers. These are low pressure phenocrysts. Well, low pressure in the mantle context. That's still pretty high pressure, make no mistake. Then we get polybaric, high pressure phenocrysts, 4 to 7 gigapascals up to 190 kilometers. Then we have this group over here, which has a different population again. So that all of these are different types of populations putting together in this histogram. So here we have the xenocrysts up to 10 gigapascals, which is up to 290 kilometers. And I've called these sole survivors from Wadsleite that actually formed right down at the mantle transition zone at 400 kilometers. Then all of these crystals were mixed together and fed into the different komatiite flows. And that's why each flow carries a unique olivine cargo. So we don't know where all these crystals came from in one flow, but they all got jumbled up and produced then nice linear mixing lines with the high temperature komatiite. So just to summarize now, what's significant about the COMMONDALE olivines? They have the highest phosphite content ever observed in terrestrial olivine. greater than forsterite 96. Highest aluminium content ever observed in a terrestrial olivine greater than 0.3% Al2O3. Highest pressure and temperature observed in any mineral phase outside of diamond inclusions. These olivines are deeper than most diamond inclusions of high pressure, except some diamond inclusions have bridgemanite, which is come from the very deep lower part of the mantle. And this is the first direct link of komatiites to the mantle transition zone. And it records a passage of the melt through the mantle. So what are the wider implications of these results? The mantle transition zone contains enormous amounts of water. This is contained in the high pressure polymorphs of olivine and wadsleyite, and high pressure polymorphs of olivine called wadsleyite and ringwoodite, which can contain up to 2% water. The water content would be at least equivalent to what is currently contained in the oceans. The question is then, over Earth's history, how much olivine has been transported and released water from the conversion of these high pressure olivine polymorphs during passage to the surface? The direct evidence of deep plumes in the Archean has now largely been obliterated, but may have been very significant for Earth's water budget. Thank you.
Thank you so much, Alan. That was really fascinating. And let's see if we have any questions. First from the audience here. Any questions from the audience?
Please tell me I'm wrong.
Alan, you mentioned that the matrix or the ground mass in the COMMONDALE KOMATIITE was celtic.
Well, not felsic, high magnesium basalt, not komatiite.
It was high magnesium basalt.
Yeah. Okay. The reason being is that the olivines continue to grow, taking up the magnesium from the melt which was contained within them, and it was that the fractionation growing these olivines which gave the zoning, which is what we see now.
Yeah, you can see the preserved forsterite.
Yeah. And then once that low forsterite content was established, it then started equilibrating right through the grain, right to the center, because of the high diffusion. But I mean, that diffusion at 1700 degrees, you would probably re-equilibrate that olivine completely in 2 days.
Are they composite flows? You see cumulate zones.
Sorry?
Are they composite? COMMONDALE KOMATIITES, are they composite flows like you see at BARBERTON? Cumulates into spin effects?
I'm just going to repeat the question for the online audience.
Oh, yes.
So Ben asks, for everyone who can't hear, if the flows are composite flows. Composite flows, yes.
So you're asking if there's, as well as the ferric olivines, whether there's spin effects as well. Yes, there is spin effects. But the spin effect in COMMONDALE does not reflect the primary melt. It's completely different. And I think what actually happened was that, even the chill margins are actually very, very low iron and low magnesium. Now, how do you get that? How do you reconcile it with the composition that I've been showing? And what's happened is that the original chill was actually reconsumed by the lava and then reacted with seawater.
Okay. Any other questions from the audience here in the room? Marina, and I'll just repeat your question, okay?
Yeah. And well, this water release, but initially this water should go into the subduction zone.
Yes.
Where is this water was from? Oh, yes, in the subduction zone, because it's very ancient subduction zone. So at the final stage, it should be merged into the transition market.
So
you can get this water. Well,
the question that Marina Yudovskaya asked is the source of the water that these olivines / wadsleyeites are sampling.
Now, Well, the paper that we did with Alex Sobolev, we showed that this was actually the signature was surface water. These contained in the melt inclusions in olivine from BARBERTON of 3.5 billion. So we proposed then that there was a subduction component right down to the mantle transition zone. And the fact is that because of the propensity for wadsleyite and ringwoodite to hold water, it means it would have actually acted as some sort of early sponge from the very earliest stage in the mantle. So we don't know where the water actually came from.
Okay, thanks, Marina. We have a question from Lou Ashwell in the chat who says, what is the ground mass around the olivine phenocrysts composed of?
The ground mass. It is composed of microus pyroxene spinifex and devitrified glass. And it's slightly evolved because it's not similar to the matrix in komatiites, very komatiites like bilingue, because those olivine crystals in bilingue actually formed in addition to that trapped melt. In BARBERTON, in COMMONDALE, the low forsyte olivines grew from that trapped melt, which is what depleted the magnesium in that trapped melt.
Okay, and then so we have a question from Ray Durheim, and then we'll get to Allan Menzel-Jones' question. Have any olivines been found in meteorites, and what do they tell us?
Yes, there have been lots of olivines found in meteorites. And in shergottites from Mars. Olivines are everywhere. But what's happened is in most meteorites, the olivines seem to have re-equilibrated quite rapidly. And so they're not as high aluminium as what we're seeing here, which is what we would have expected, but it has not been found.
Okay, and then we have another three-part question from Allan Menzel-Jones, who is interested in the water budget. And so the first part of the question is, surely water loss from subducting plates as PT increases, is the fusion rate slower than subduction rate? And what happens to that water that exsols from the wadsleyite when it converts to olivine? Where does that water go? Is the second part of the question. That's Allan Jones.
Okay. Water lost from the subduction plates. Yes, it is, of course, but it's still believed to be, the water still is carried down in high pressure hydrous minerals, which are then assimilated or become incorporated into the mantle transition zone. The subduction is, what we don't know is if subduction was the same in the Archean as it is now, but there is plenty of evidence that subduction now goes as far as a transition zone and possibly into the core mantle boundary. But maybe this will help elucidate actually what does happen with water in these subducting plates. What happens to the exhaled water at 400 nanometers? Wadsleyite converts to olivine and well, the water just goes straight up out of the system. And these komatiites probably actually had some appreciable content of water in them. This opens up a whole debate on how dry komatiites were. At one stage, it was believed that komatiites were 100% dry. There was no water there. But this has now been modified quite extensively that all komatiites contain some water, and possibly the COMMONDALE komatiites have much more water than other komatiites. Do you see any hydrogen differences in the olivine, or has? Well, we're trying to actually measure these things. The hydrogen content, the protons in olivine is actually a measure of the water content. Now the only way you can do this is with Fourier transform synthesis, and it's very difficult, and there are very few labs that can do it, and we are trying to actually get labs to be able to do it on these olivines at the moment.
Okay, thanks. Thanks for that, Alan. And we have another question in the audience, nice and loud, check.
So you said that these olivines, COMMONDALE olivines, they have high aluminum contents, and these are coming from deep mantle. Okay, so do you expect that these kind of olivines may have been sampled by some other lavas, or, other KOMATIITES, or if not, why not?
Okay, I think that the question you're asking is, do we see similar high aluminium, high pressure olivines in other KOMATIITES?
Yes.
Well, this is actually a two-part answer to this. First of all, these very high olivine, these very high magnesium olivines are very difficult to preserve.
Yeah.
I mean, the KOMATIITES are not, they're also very rare worldwide. You don't just, they're not like Karoo basalt. You go and, and secondly, the question is, have we really looked in these other KOMATIITES for high pressure olivines? And in fact, we are now looking at these in Barberton much more rigorously to see if we can preserve, this whole mixture of olivines as cargo. Then we might just find in one slide of Barberton, you'll find one olivine which has got high aluminium. We don't know. Now the problem is there's no way of identifying this. You've got to probe every single olivine throughout the whole slide to find out where these things are.
They might not be preserved in the composite because of the constant flow of heat.
Yes.
Yeah, and maybe
Yes.
maybe you can find in some diamond inclusion. Don't know.
Sorry, what?
Maybe it may be preserved in diamond.
Oh, you're asking all the right questions. No, you can't. The temperatures are much too high.
Oh yeah.
No way will you get diamonds in this magma. No way.
And then,
hundreds of degrees high, too high for diamonds.
Then we have a question from Marlena Elberg in the chat who asks, what happened to the first stage melt of the plume? Is that also preserved in Commondale somewhere?
No. No, it's not.
Okay.
We don't know where it went. Don't know where it went.
Okay. And then we've got one question from Roger Gibson through WhatsApp. So we have questions from all sorts here. The model that you showed, Alan, shows a continuous feeder and super fast low viscosity melt, but doesn't the texture requires staging chambers to give time for crystallization at different depths and then entrapment in the next batch of melt?
Yes, good question, Roger. I think the olivines came up at different rates because what I didn't go into is that the aluminium zoning is not always constant across every grain, and some of them show a nice gradation from high aluminium in the center to low aluminium in the margin. So those could have grown more slowly as the melt came up, and there probably are staging chambers because there are also clusters of olivine grains, but none of these are very, very high aluminium. They're all relatively low, so I think there were staging chambers much closer to surface. But what these potential staging changes could look like at great depth, I have no idea.
Okay, thanks, Roger. And then I'm going to end off with a slightly different question from Erin, who's joined us. And Erin really wants to become a geologist, it seems, and is wondering what got you into geology. So I think that's an appropriate question to end on, non-scientific, but super important for non-geologists watching, or students watching.
Well, I'll tell you, it's very, the answer to that's very simple. That when I started my degree, I wanted to be an astronomer and a physicist. And I was doing physics and maths and chemistry with my colleagues who were doing geology, and they were all going off on these nice field trips and talking about the nice things they could do. And I thought, I'm really losing out on this. Why can't I do something which combines chemistry and physics and go on field trips? And that's how I got into geology. Simple as that.
And I think many of us in the room would agree. Fieldwork is certainly a great part of this job.
Yeah.
We're glad you converted, Alan. Right, so thank you everyone very much for joining us for this talk, and Alan, thank you for giving the talk. And you can look out for Alan's paper on this, which will be published in 2 weeks' time in Geology. So You heard it here
Well, it'll be
first.
it's a pre-publication, but if somebody wants it, just send me an email and I'll send you a copy of the pre-publication.
Thank you, Alan, for being willing to give that talk for us. And then next week, we have a talk from Sarah Payne, who is working as a researcher within Chimera, and she's talking about, her topic is identifying potentially remaining mineralization in the Wits Basin using the National Resource Atlas. So that should be a very interesting talk for all of you interested in mineral deposits and what can still be mined in some of our important mineral deposits. So thanks everyone, and we'll see you same time, same place next week. Thank you all.